Orthogonal expansions, a great Maple add-on. Where an introduction normally sits, you'll find the abstract, which I assume everybody attending this webinar has read. Otherwise, why would you be attending? So instead, I'd like to begin with an anecdote about Dr. Jerry Uhl. That's UHL. He's the author of Calculus with Mathematica. Jerry was at the University of Illinois in Urbana-Champaign in the middle of Illinois, just 90 miles from Rose-Hulman Institute of Technology, and it was reachable in 90 minutes. Sometime in the late 1980s, Jerry invited several of us from Rose-Hulman to visit him at his home on a Saturday morning to show us his ongoing work on the calculus with Mathematica. Jerry's vision was that with such technology, the way mathematics was taught and learned and practiced should change. And according to his lights, he was working out how it all should change. Technology was just a tool by means of which changes in the curriculum could and should be made. Jerry did it his way, and I, just about a year younger than Jerry, worked it out as I saw how it should be done with Maple. But the meta vision was the same. Use technology as the instrument for curricular change. Now, about 10 years later, at a pre-session to a math fest that was held in Toronto, I think it was 1998, Jerry gave a talk that I missed, but I was able to read a copy of the talk. In effect, he said bluntly that if we didn't change how we taught math to the consumers of mathematics, we wouldn't have any more such consumers. I've never been able to track down a written copy of that talk since then, but as I understood it, when Jerry gave that talk, he railed against what I described as the discreditive biological principle, ontology recapitulates phylogeny, which means that as an animal develops, it goes through all the stages that its species experienced in evolution. So what is the analogy there? It's what we do with our math students. In their training, we drag them through the centuries-old evolution of mathematics and mathematicians. So this webinar today explores the tools in the orthogonal expansion package written by Dr. Sergei Moiseev. Now, I asked my neighbor who's a Russian, I have a Russian neighbor, how to pronounce that name. And it's like 3.5 syllables. Boy, both vowels are kind of pronounced Moiseev. It's the best I can do. So if I've mispronounced his name, I apologize to him. He's done a great work in this package. So I'm looking at this package from the perspective of teaching boundary value problems. So in the boundary value problem course, look at all the things that you have to encounter. Orthogonality of functions, function spaces, L2, different orthonormal series. It's a lot of work. You got sines and cosines, which is Fourier series. Then you got Bessel functions, and you got Legendre polynomials. All of those things come up, maybe even more. These tools in this package, they really help getting through that material. And it is my belief that the only real way to get this stuff done is to make use of technology rather than drag through all of that classical material, which takes so long to absorb. So let's see how it works. We'll begin with an initialization. We'll put the package into place with orthogonal expansions. I assume that the package has been downloaded and placed in the appropriate location. If you download the package, you can get the link from here or here. It's stored in the Maple App Center. The instructions for how to install the package are there. So I will assume that this is in place. And when we talk about the Legendre series expansions, this package uses this particular branch cut for the Legendre functions. So let's take a look at this package. We'll give a quick outline of the package before we give examples. There are 18 commands in table 1. You can see things like Bessel series, Fourier series, Legendre series. So these commands will give series expansions either a formal expansion out to infinity or a finite sum to an arbitrary n or a specific n. So you don't have to go through all of the process of obtaining coefficients and making a sum. You just get the series. You can throw it into a plot command, and you can see whether or not the expansion is behaving as it should. Table 2 shows the options for example, the Fourier series command. These shaded boxes are options that are pretty much available in these other series commands. And this one here should be noted. If you have coefficients that cannot be obtained because the integrals can't be evaluated, you can switch to numeric evaluation within the command, within the call. All you have to do is put the option output equals numeric, and you don't have to know all of the Maple syntax for making that happen. You can see down here if these two options control the integrations. Very, very helpful because it eliminates a lot of the syntax you would otherwise need to make this stuff happen. Table 3 is an example of the calling sequences for something like Fourier series function, the set over which you want the expansion, the number of terms you want in the expansion. Now that n could be the symbol infinity or the word infinity. You get a formal sum. You can put also a Maple name. It doesn't have to be coefficient name. It can be a letter like C. That will be the recipient of a list of coefficients. So you can see that in operation, these commands that are up in here in table 1 are very easy to use, very, very simple, make the job of obtaining the series and looking at its behavior very, very simple. Table 4 lists 2 additional commands. There is a Gram-Schmidt command, and it's different from the Gram-Schmidt command in linear algebra, which is applicable to vectors only. This has the appendage on the name L2. It will orthonormalize functions. Really, really interesting, useful command. Then there is the mixed series command. Applies for multi-dimensional expansions. So you have a function of several variables. You want to expand the first variable in one polynomial basis or one function basis, and the second variable in a different orthogonal basis. So this mixed series will do that. Otherwise, if you had to do that by hand, you have an awful lot of bookkeeping to deal with. Table 5 lists 6 commands that generate specific orthogonal functions, not necessarily the sequence expansion, but the functions themselves. For example, Haar, you get the Haar wavelet, harmonic wavelet, rational expansion in terms of these functions. I guess you can call them wavelets. The sinc wavelet, the Walsh functions, Zernike. Now, I've never run across Zernike, but here is a way of jumping in, seeing what the functions are, playing with them. Clearly, one can define piecewise functions in Maple, but rather than spend the time to have to do that and figure out how to get it into Maple, you have a way of just asking for it. And these are the orthogonality relations for these functions. I want to point out that Bessel functions, Legendre polynomials, Chebyshev polynomials, a few more, are not specifically generated by commands in this package. So you have a command to generate the Haar function, but you don't have a command in this package to generate Legendre polynomials or Bessel functions. So for the orthogonal polynomials, you use the orthopoly package. So that stuff is listed here in table 6. That package gives you access to Gegenbauer polynomials, Hermite, Laguerre, generalized Laguerre, Legendre, Jacobi, and the 2 different forms of Chebyshev polynomials. Now, the Jacobi polynomials are like a superset. They include Gegenbauer and Legendre, so the names are doubled up here, P, P, L, L, because one is contained in the other. And they can be accessed by these capital letters. So the function name is H. Here you can get the help page hyperlink. So you would want to see, if you want to see what the polynomials look like, use the orthopoly package. So we just mentioned Bessel functions, Legendre polynomials, and so forth. Polynomials can be seen if you go into the orthopoly package, but Bessel functions are not polynomials, nor are sines and cosines, for that matter. So when you're talking about Bessel functions, you got J, I, K, Y, Hankel functions, 1, 2, Struve functions, H and L. Maple has these. So these are in Maple, top level stuff. These are the names of the functions. If you need to access them at top level, you can explore Bessel functions. So let's now look at the Fourier series implementation in this package. First of all, the command itself, Fourier series command. Here are the calling sequences. Fourier series. So what you're saying to Maple here is, give me the Fourier series for this expression, this function, on this range, alpha to beta, using the members of the orthonormal basis from M to N. If you just put an N, it assumes that you're starting with M equals 1, so from the beginning. The N can be an infinity, you get a formal sum. You could put a name into which the coefficients will be placed so that you can see what the coefficients are separately from the expansion, and then you have various options. All right, so then if n is a finite number like 5, then you get a partial sum to 5. If it's an indeterminate like n or infinity, you get a formal sum. In table 8, lists the various options that you might access, and the list of coefficients would be assigned to this name C. Now, the definitions used in this package are a little bit different from the ones that I would use when I was teaching Fourier series. The length of the interval is D, normally called L. You don't divide it by 2. And so that means down here, D over 2 puts a 2 in these trig functions. And then you have to remember that the way they define A0 is 1 over D, and the A and the B are 2 over D. I used to make sure that these integrals were always the same, and I put A0 over 2, but here it's just A0. So you need to get that stuff straight when you're going to make use of this stuff. Here is the difference if you're using either a cosine series or a sine series. D has the same meaning. The A will be computed this way. The series will be A0 plus a sine series. The B's will be computed this way. There's no A0 here. Okay, so you would need to get this stuff straight when you want to use these tools. There's a polar form. If you recall trigonometry, you can convert A cos omega t plus B sine omega t. In Maple, there is a command, convert phase amp with respect to t, and you put it into this combined form where it's a cosine omega t and a phase angle. And the magnitude is square root of some of the squares. So that's all that this polar form is. It makes use of this trig relationship. There's the exponential form. Here is how you compute the coefficients. Some books just use a single exponential, and they let k run negative and positive. Here, two separate exponentials, one for k positive. Well, k is always positive here, and these are the two exponential functions that you need with exponential form. And there is this thing called Hartley form, which I had never seen before, where the basis functions are cos plus sine, cos minus sine. And those are options that you can give to the Fourier series command to amplify how you might generate the particular Fourier series that you want. I think it'll be much more satisfying to see a few examples. So let's obtain the sine cosine series, Fourier sine cosine series for e to the x on 0, 2. Define D, ask for the Fourier series of e to the x from x equals 0 to 2. We'll take n equals 2, so we'll just get a partial sum and assign the coefficients to the name C, and assign the partial sum to the name capital F. So here is what the Fourier series partial sum looks like. Here is a list of lists which gives the coefficients. This is A0. These are the two A1 and B1. This is A2 and B2. If you say n for the number of terms, then the list of coefficients, I've given a different name. This is A0. Maple doesn't know how many terms you really want, so it gives you a sequence of coefficients. So this then gives you the general form of the sequence of A's and the sequence of b's. Now, if you did this by hand, a0, a sub k, b sub k, you do the integrals yourself, you would see that the a k's match this. This package uses small I as its counting index. I like k for my counting index, and these match. And here is a graph, e to the x and the partial sum that we created, and you can see that the partial sum begins to look like the function. Here's a second example, a Fourier series, sine series, cosine squared on 0 to pi. So you make use of this Fourier series command. What are you getting the series of? Cos squared, 0 to pi. Let's go out to n equals 6. And the way you get a sine series, you say series equals sine. Here, I'm doing the calculation. I want the formal sum, and I want the coefficients. And I put a colon here. I don't care what I see here. I want to see what the coefficients are going to look like. Well, this is not in as simple form as it could be. Here's a simplify, and what is this op thing doing? It's going inside this bracket, go inside the sequence, and it's grabbing this stuff inside. And you see that the coefficients are given as a piecewise function when I equals 0, I equals 2, 0. This otherwise. But look what happens over here when I equals 2. You get a 0 in the denominator. So if you do the naive approach in Maple by hand, you better know your calculus, because the formula for the coefficients depend on the value of n. The formula here is invalid when n equals 2. And if you don't know that and simply throw this thing into a sum, you have an I doesn't belong there. And if you use add instead of the sum, you get a division by 0, because here what happens, Maple in the add command, Maple evaluates n for each term, and it realizes, wait a minute, I'm dividing by 0 here. So at the top level, to get this thing right, you would need to use the all solutions equals true option in int. So not only do you have to know your calculus, you have to know something about Maple, and you have to use int. There's no way to use this 2D symbol for integration and get this all solutions equals true. So this command for a series does a really good job of getting students over these kinds of difficulties, where for some values of the index, the coefficient is undefined, because the integration formula is specific to values not equal to certain bad values. Here's a third example. We'll get the sine series for e to the x cubed. That's picked because the integrals of e to the x cubed against trig functions can't be done in closed form. And what happens here is you get a formal sum, and you see that the coefficients are these integrals. If you look here, if you add the option output equals numeric, you don't have to change anything except add that option, and the integrations for the coefficients are done numerically, and so you get a partial sum that you can work with. And this is the graph of the partial sum against that function. You can see it's going to take a lot more terms than we've computed. We've computed 3 to get convergence. And here, if you do the integrals essentially by hand, letting Maple do it, you have to eval f around the integral. And you can see here that these coefficients match the coefficients that the Fourier series command came up with. And now a fourth example of these Fourier series. I'm going to do a sine series of this function of 2 variables. So I picked this function of 2 variables, each variable is 0 to pi. This is the function, and I want to show you what the function looks like. Plot 3D. Just a little bump. To get a Fourier series in 2 variables is a lot of work. I don't know if you've ever done one. You've got a lot of bookkeeping to do. The Fourier series command does that bookkeeping for you. 0 to pi, 0 to pi, 3 in the first set of functions, 3 in the second set of functions, and series as a sine series. So you get sine, 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 1, 1, 1, 3, 3, 1, 3, 3. The even ones disappear. If you do it to n in one and m in the other, you will get a formal sum. Interpreting this takes a little bit of patience. You've got 2 indices, k1 and k2. You've got 0 or 2 coming out of this. Oh, I guess minus 2. And 0 or 2 coming out of that. 2 indices. Over here, this I goes from 1 to 2. So this subscript means k1 or k2. This subscript means the first member of the list or the second member of the list. That's what it means down here. So with care, you can get the full formal expansion. Over here, if you take this partial sum and graph it along with the function itself, you see that the few terms that we took, one in red and one in green, they're so intermingled that you can conclude just from the picture that it's a pretty good approximation. So in a boundary value problem course, Fourier series typically comes first. Next, you meet Bessel series. The last one that you meet is Legendre expansions, because Bessel comes up in cylindrical coordinates and Legendre in spherical coordinates. Now, you're doing Bessel functions. There's a couple of things in Maple that help. There's a command called Bessel J zeros, and it represent the zeros of the Bessel function. So I alias to lambda to make things more compact. And this typesetting command allows Bessel J and Struve H function to have to display as the letter J or the letter H. So if we do a formal expansion of a function in terms of J0, so Bessel series, function, domain, a range of 0 to C, arbitrary number of terms so you can get a formal sum, and 0 is the J0. Right? So you can see here, these are the integrals that give you the coefficients against these functions and this is part of the normalization. Now, Maple is able to evaluate integrals of the form x squared j0, and this is the appropriate eigenvalue, and we'll do it in terms of Struve H functions whose shorthand notation that we did here is h0. So if you want to do the expand the function, say x on 0 to 1, you can get a Bessel series with this command. Bessel series x equals 0 to 1, 3 is the number of terms, this is j0, and so you can see j0, j0, j0. The lambda 0, 1 is the first eigenvalue of j0. And here lambda of 0, 2 is the second eigenvalue of j0. This is the third. And inside here, these are the evaluation of the coefficients in closed form. You see you get j1 and Struve H. So you get this without a whole lot of discussion about how to do all of this stuff that takes days to drag through. And then you get a partial sum that you can take a look at and see if it's useful or not. So if you use the numeric option, the sequence of eigenvalues can be obtained here. This is a shorthand for Bessel J0s. So these are the eigenvalues, first three. You can expand this function x in a Bessel series using output equals numeric. This is then what the partial sum looks like, and you see here 2.4. These are the eigenvalues: 5.5, 8.6, and then you want to draw a graph to see what things look like. This is a graph of this Bessel series. Kind of looks like the line y equals x. After looking at Bessel expansions, Legendre polynomials are the agenda. So let's look at just Maple, the Legendre equation in Maple. All right, where does it come from? You separate variables, del squared u equals 0, Laplace's equation. You do it in spherical coordinates. You do all that separation variable, Sturm-Liouville stuff, and you will get either Legendre's equation or Legendre's associated equation. You notice here that this Legendre equation is the associated equation with this parameter m equals 0. So Legendre's equation has two solutions, second order, and those are called solutions of the first kind and of the second kind. The first kind is called Legendre P, and the second kind is called Legendre Q. Typically, for these singular problems, because you got this x squared as a coefficient, you're going to get a logarithmic solution as the second solution. So Legendre Q, the one logarithmic solution. So in Maple, you can get this function as Legendre P and x. It's also in the orthopoly package as P of nx. It's also available as Jacobi P n 00x, or orthopoly P n 00x, as we took a quick look. So it's available in Maple in several ways. Legendre polynomial. If you want an expansion in terms of these Legendre polynomials, you would use in orthogonal expansions. This syntax is your function. This is the range over which you want the expansion. Number of terms. That 0 is this m equals 0. If you are expanding in terms of associated functions, it's Legendre P n m. You need two parameters. And in the orthogonal expansions package, you would have an n and an m. And remember, the Jacobi polynomials contain all of these. For various values of the parameters in Jacobi, you get these guys: Legendre, Gegenbauer, Zernike, Chebyshev. It is confusing because the mathematics is confusing and complicated and interrelated. Now, a quick reminder of what Legendre polynomials look like. This is just maple stuff. So here are the Legendre polynomials accessed by Legendre P. Just get a sequence of them, and then I print them one under the other so they're easier to see. If you take powers of x on -1 to 1 and Gram-Schmidt them, so you're orthonormalizing. So I'm using this Gram-Schmidt L2. You get multiples of these. These and these are not the same. The normalization is different. Legendre polynomials are normalized so that they all are 1 at x equals 1. That is not the case for these functions, these polynomials, who come from Gram-Schmitting. At 1, they are not 1. They are orthonormal. Here are the integrals of their products. They are orthonormal. These are orthogonal, but not orthonormal. It's the same with sines and cosines. Sines and cosines in a Fourier series, they shift the normalization constant. They don't split it evenly on each function. It's for convenience. And so here it's 2 over the odd numbers. So the integral of the product of the Legendre polynomials will give you either 0 or not 1, but 2 over the odd numbers, 2k plus 1. And so when you go to compute coefficients, you shift that factor out front of the integral, just like you do for sines and cosines. 2 over L, 1 over L, that's where that comes from. And so an expansion, in terms of Legendre polynomials, you have the coefficients, but the coefficients are computed this way. So now let's actually do a Legendre polynomial expansion. I've got 2 examples here. Here's a first one. Let's get a Legendre series expansion of e to the x. We'll do it on -1 to 1, which is the natural domain for Legendre polynomials. We're going to go 3 terms. You got to put 0 here. That's the m equals 0, and we'll collect coefficients here. I hit it with a simplify to get these Legendre P functions to be expressed as actual polynomials. That's the second line. And here is the list of coefficients. Graphical comparison. E to the x, this expansion, one in red and one in black, you can hardly tell them apart. Very, very interesting how well that approximation takes place. E to the x here, same stuff, different name for the list of coefficients. Output equals numeric. Now you have a numeric expression. If you ask for a sequence of Legendre polynomials computed by the appropriate formula. And then you compare that to the coefficients obtained by the Legendre series function, you'll see they're identical. And if you add these coefficients that we compute by hand in a linear combination of the Legendre polynomials, but notice I shift the index because sequences and lists in Maple start with 1, not 0. So you got to do that so you don't get errors. And they're the same. So the Legendre series command saves you a lot of work of computing coefficients and making sums. Just gives you the result. Here's another example. Example 6. Let's get a Legendre series of root x from 1 to 3. Now remember, Legendre polynomials are defined on -1 to 1, and I'm going 1 to 3. So there's a lot of shifting back and forth you have to do. I'm going to take two terms. The 0 is for the m equals 0. G will be where I'll put the coefficients. And so this is what G looks like. It has Legendre P. If you say simplify, then the Legendre P is replaced by a polynomial that looks like a polynomial. If you collect and simplify this thing, then you get powers of x. And here is the list of coefficients. Again, a graph of root x and g shows very, very close. But I'm here giving the algorithm for shifting. So if you want to expand a function f on a to b, the Fourier-Legendre series, you need this transformation. You find x of y, a plus b, b minus ay, all over 2. You expand f of x of y. You place your x's by this thing in a Fourier-Legendre series because the y is going -1 to 1. And then, to get what you want, you take that result, which is in y, and you place y by y of x, so you have to solve this thing for y as a function of x, which is what this is. And if you do that by hand, for this example, x will be 2 plus y, and so your Legendre series is root of 2 plus y, where y goes from -1 to 1. I take two terms, m equals 0. And then when you come back, you take that result and you replace y by x minus 2. And if you compare, you see that everything checks out. So the beauty of this command here is that you don't have to go through these shifts, and that's true for all of these commands. That's why I say this is a marvelous package. This is a really, really useful package. What's a Haar wavelet? And what would a Haar wavelet series be? Well, this was something I had only briefly seen while I was still teaching. I plugged this package allowed me to play with it. Haar wavelet. This is the way it's described. Scale n, shift j. Now, one could easily define this piecewise function in Maple, but the command Haar njx in this orthogonal expansion package produces this expression. There is this restriction on j. Why is that? Well, if you look here, you're dividing the interval 0 to 1 into these little bitty pieces, and this last one can't get bigger than the right endpoint of 1, So if you look at this condition and solve this inequality for j, j has to be less than 2 to the n minus 1 in order to keep this in the interval 0 to 1. They are orthonormal on 0 to 1, but the orthonormality condition is strange because each function has two indices, nj, mk. So n has to equal m to get a 1, and simultaneously j has to equal k to get a 1. Otherwise, you're going to get 0. Now, I thought I would explore some of these functions, so I ended up doing this explore thing. I let n go from 0 to 6 and j go from 0 to 6, and you'll see if you violate this restriction, you'll get an error. I'd like to see what happens. So let n get big enough. So you see n can be bigger than j. So n gets bigger than j. Well, they get skinnier and they move to the left. This moves them to the right because the shift thing doesn't change the height. See, this is called scale, and that's what makes them go up and down. If you don't pay attention to the inequalities, you'll get an error. Okay, so you can play with these Haar functions to get a sense of what they look like. So what would a Haar series look like, and how much work do you have to do to get one? Well, here's the Haar series command, calling sequences. A to B, not necessarily 0 to 1, you can go A to B. And the start and the end of the functions that you're using, these are the coefficients. And if you just say n, it's equivalent to starting at m equals 0. And how do you get these coefficients? You need a length of the interval, d. There's a c0. And then the rest of the coefficients are doubly indexed, so there's an ij. So there are two parameters here in the Haar function. And you have a sum on I from m to n, and a sum on j from 0 to 2 to the I minus 1. So this is a rather complicated looking expansion. I needed an example of this. This was mystifying to me. So I took e to the x on 0 to 1, as simple as I could. 1, so I got 0 and 1 for the terms, and a list of coefficients. This is what it looks like. Well, it's hard to read that. And here's the 0 term, and then you have a first term, and then you have two terms. If you simplify, you get this completely written out piecewise function. So you're going from 0 to 1 in steps of a quarter. You're going 0 to 1 in steps of a quarter. So this is like a step function approximation to e to the x. And here you see what it looks like with the curve e to the x. Here they are both drawn, but discount equals true, so you don't get these vertical connectors, and you see the approximation just piecewise constant. I'd never seen that before. Okay, so then let me compute some of these coefficients. The c0 is e to the x. That's this one. then you have a 0, 0 term, a 1, 0 term, and a 1, 1 term. So Haar 0, 0, Haar 1, 0, Haar 1, 1. And you do the integrals. This matches this. 1, 0, 1, 1, that's what these two guys are. And these match these numbers. In fact, I needed two examples to even begin to get comfortable with this thing. Haar series, e to the x on 0 to 2. I'll go out to 3 terms. N equals 3. Here's the list of coefficients. And I'm going to work numeric because the expressions get too messy. And I do the simplify so I get this combined piecewise function. And you notice it's now by 1/8. Here I've got to 1, and here I've got to 2, and I'm going by 1/8. And if I graph the e to the x and the Haar expansion on 0 to 2, I'm using 0 to 8 to bound the y-axis. Discount equals true. You'll see piecewise constant approximations, and they spread out more and more as you go up. That's what it looks like. Let's get some of these numbers here. I got the coefficients, and I chopped down the number of digits shown, and I have the C0 and then the 1 and 1 1 1 1 0 1 1. Now here are 4, and now here are 8 of them. What I had to think about this. This was not easy to. This didn't jump into my head right away. C0, C0 0 0 1 0 1 1, 2 0 2 1 2 2 2 3. 3 0 3 1 3 2 3 3 3 4 3 5 3 6 3 7. See, this is 2 to the n minus 1. So 2 cubed is 8 minus 1 is 7. So this second index goes out to 7. That didn't jump out at me. So here I'm eval f of the integral, so I get floating point numbers. F normal, so I don't see so many decimals. And then I did an explore, and by you got to have n and j. So I did an explore to see if I could recreate these coefficients, and it does. This explore is a table inside a table, and I tried stretching this thing here, and it doesn't stretch. It's just a nuisance. Maple could approve this. Is there one of these guys that's an 068? It's in here somewhere. It's 3. It's in here. Oh, it's this one. Okay. So you can play with this guy, and let's see, go smaller here, you go here, you get this 05 one, I believe that's this guy here. Okay, so recreate those coefficients just to see what's going on with this Haar expansion, piecewise constant approximation. I'm sure there's a whole theory for why you sample in this fashion, but I just wanted to get some idea of what does this Haar expansion look like, and the tools in this package and using Maple gives me some insight into what this Haar stuff is all about. See, then this orthogonal expansions package had this thing called a rect series. Basic function is just 0, 1. And you do expansions in terms of forms of that basic function. And this is what a series looks like. And the calling sequences are rect series function, the range A to B, where you want to start, where you want to end, some place to dump the coefficients. And if you just put n, it's equivalent to saying m is 1. And then clearly we want to do an example. Well, here's an example of a rect series. Let's see what this thing looks like here. We'll do it for sine x on 0 to pi, so we know what that looks like. It's this little arch. 5 terms, place to put the coefficients. This is what this rect series looks like. It's all of this stuff here. Okay, so you do is simplify, and then you get a piecewise expression, 0 to pi. Looks like pi upon 5 are the steps. This is what the graph looks like. So it's a piecewise approximation with constant values. This is the list of coefficients. I needed to define a rect function. I don't think this package has that in it, because otherwise you just got rect when you ask for an expansion. So I did this simple piecewise function, called it rect, and then everything worked. Did a sequence of the coefficients. This is how you compute the coefficients. If you do those integrals, you get the same coefficients as are in this list that the rect series command produced. So there's a lot more stuff in this package, way more than you can go over in an hour. Good set of tools. I think it's unfortunate that a set of tools like this is not inherent in Maple. Maybe someday they'll be in there.